December 17th, 2025. In less than 48 hours, just 43 hours from now, the interstellar object 3I Atlas will make its closest approach to Earth. Astronomers have now logged a 14th anomaly, and some features don't look natural. This is the closest, and possibly the last chance humanity will ever have to study this visitor from beyond our solar system. For months now, since its initial detection back in early July, we have been tracking this enigmatic traveller as it traces a hyperbolic trajectory through our cosmic neighbourhood, a path that mathematical analysis confirms will eventually sling it back outward into the interstellar void from which it came, never to return to our sun's gravitational influence. But as this object rushes toward us, accelerating under solar gravity toward its moment of closest passage, it has been exhibiting behaviours that contradict every baseline expectation we hold about how inert rocks or simple comets should conduct themselves when exposed to stellar radiation and gravitational forces. Before we go 1 second further into this analysis, if you're following this story, if you want real-time updates as observation data floods in from telescopes worldwide during the critical 48-hour window we are now entering, you absolutely must subscribe to this channel right now and enable all notifications. We are going to be posting immediate analysis as spectroscopic data, as high-resolution imagery, as trajectory measurements come in from facilities across the globe during closest approach. This is time-sensitive coverage of what could be the most significant astronomical event in modern history. Hit that subscribe button, turn on notifications, because what happens in the next 2 days could fundamentally alter our understanding of what travels through the space between stars. Now let us examine exactly what is happening with this object and why a study published just hours ago has sent shockwaves through the astronomical community. This visitor from beyond is speaking to us, communicating through the universal language of physics and light, transmitting information through its motion and its emissions and its behaviour under the laws that govern all matter regardless of origin. And the message it is sending, the story its physical properties are telling, is becoming increasingly difficult to translate using our standard dictionary of planetary science. Our comfortable framework of assumptions about how natural bodies should behave when they fall through stellar systems after millions of years journeying through the cold dark between the stars. Tonight we are examining a breaking development that fundamentally changes the entire conversation surrounding 3I Atlas, a newly published study that appeared in preprint form mere hours ago, analysis that has been under embargo while researchers verified and re-verified results that seem too strange to be credible, too perfectly anomalous to reflect accurate measurement. This study has analysed in unprecedented detail the behaviour of the object's anti-tail, that mysterious sunward-pointing jet of material that has puzzled and fascinated astronomers since it first became apparent in early observations that this was not behaving like typical cometary tails that stream away from the sun pushed by radiation pressure and solar wind. We have known about the existence of this jet for months now. Observers around the world have documented it in images spanning the visible and infrared spectrum, have tracked its evolution as the object moved through different phases of its trajectory. But what we did not know, what we could not determine until sophisticated motion analysis stripped away noise and isolated the pure signal hidden in the raw position, data collected during July and August observations, was exactly how that jet was moving, what subtle variations in its orientation and intensity revealed about the source mechanism driving its formation, and about the object's underlying structure and rotation state. Let me provide context for why this matters so profoundly, why understanding the motion of this jet is not just academic curiosity, but goes to the heart of whether we are witnessing something natural or something that challenges our categories. When we observe comets, when we study the objects our solar system produces through billions of years of accretion and collision and thermal processing, we expect chaos. We expect tumbling, random orientation changes driven by the asymmetric forces created when localized regions of ice sublimate under solar heating and eject material into space like natural rocket thrusters firing in uncontrolled directions. We expect jets to erupt from active regions scattered randomly across the surface, vents that rotate into and out of sunlight as the nucleus spins, creating sporadic, unpredictable emission patterns that vary on timescales of hours as the body tumbles. A comet in our standard understanding is essentially a dirty snowball, an aggregate of ice and rock and organic compounds held together by weak gravity and perhaps some cohesive strength from frozen volatiles acting as cement between components, tumbling through the darkness on whatever chaotic rotation state billions of years of random perturbations have imposed. When sunlight strikes a pocket of volatile ice embedded in this structure, when solar heating penetrates the insulating dust layers covering the surface and reaches temperatures sufficient to drive sublimation, the ice transforms directly from solid to gas without passing through liquid phase, expanding rapidly and blasting outward through cracks and pores in the overlying material, like a chaotic thruster, igniting and then sputtering out as rotation carries that region back into shadow. That is the baseline. That is what nature usually produces when you have an irregular aggregation of materials with different thermal properties and different volatile content tumbling randomly while exposed to the intense directional heating of a nearby star. Random chaos, unpredictable variation, sporadic outbursts that don't maintain consistent directionality or intensity for extended periods. But 3I Atlas, according to the new analysis that has just been published, is doing something fundamentally different from this chaotic baseline expectation. The study reveals a distinct periodic wobble in the anti-tail jet, a rhythmic predictable oscillation that this is not the random sputtering we associate with melting surfaces on tumbling bodies. This is structured variation, periodicity that indicates stable underlying geometry, rather than chaotic processes. It is pattern where we expect noise, order where we anticipate randomness. By carefully tracing this wobble back to its origin point, by using the motion of the jet material as a probe that reveals information about conditions at the source, researchers have pinpointed with remarkable precision where on the nucleus this emission is originating. And the data, cross-validated through multiple independent analysis techniques to ensure robustness against systematic errors, indicates something extraordinary. The jet source lies within just 8 degrees of the object's rotation pole, the axis around which the body spins, the geometric point that remains stationary while everything else on the surface rotates around it. Now let me explain why this single geometric fact, this seemingly technical detail about angular position relative to rotation axis, matters so profoundly that it has prompted emergency discussions among trajectory specialists and theoretical astrophysicists who are scrambling to understand implications. The reason this location is significant, the reason 8 degrees from the pole is not just another random position, comes down to pure geometry and to what that geometry implies about orientation. If the jet is emanating from the pole, if material is being expelled from a location that sits almost exactly on the rotation axis, and if simultaneously that jet is pointing directly at the sun, which we know with certainty because it forms an anti-tail structure extending sunward, rather than being blown back by radiation pressure like normal tail material, then through simple geometric reasoning we can deduce something profound about the object's orientation in space. The rotation axis of the object itself must be pointing at the sun. The spin axis, the invisible line around which the entire body rotates, is aimed like an arrow directly at our star. Let me provide an analogy to make this configuration viscerally clear. Imagine a spinning top, that classic children's toy that demonstrates gyroscopic stability through rapid rotation. Normally, when you throw a rock into space, when you launch any irregular object without active stabilization, it tumbles end over end, rotating around multiple axes simultaneously in complex chaotic motion, determined by whatever angular momentum it acquired during launch, and by subsequent perturbations from gravitational torques and impact events. It is three-dimensional chaos, orientation changing continuously in unpredictable ways. But imagine instead a top that is lying on its side, horizontal rather than vertical, with its central pivot point, the geometric center around which it spins, aimed directly at a light source. That is the configuration we are seeing with 3I Atlas. It is spinning, yes, maintaining rotation that we can detect through periodic variations in brightness and through the precession wobble of its jet. But that spin is organized around an axis that points at the sun, maintaining this orientation not just for hours or days, but apparently for months as it has fallen through millions of kilometers of space approaching perihelion. This geometry is not just unusual. It is extraordinarily unlikely if the orientation is random, if there is no mechanism actively maintaining this alignment against perturbations that should have randomized the rotation state over the object's long journey through interstellar space. In the chaotic environment of the galaxy, where objects get kicked by gravitational encounters, where asymmetric outgassing creates random torques, where impact events from dust grains impart angular momentum in arbitrary directions, objects do not just naturally settle into perfect alignments with distant stars. They tumble, they randomize, they lose whatever special orientation they might have started with. The probability of a random object, an interstellar visitor that has travelled for potentially millions of years through the void before entering our solar system, having its rotation axis aligned with the Sun by pure chance. When we happen to observe it, is estimated through straightforward geometric reasoning at approximately 0.5%. That is 1 chance in 200. 1 in 200 objects arriving at random might show this configuration purely by coincidence, by the luck of where they were pointing when they entered our detection range. Now 0.5% is not impossible. It is rare, but not absurdly so. If we observe enough interstellar visitors, eventually we should see one that happens to be aligned this way through pure chance. But here is the critical context that transforms this from interesting curiosity to profound mystery. We have only confirmed 3 interstellar objects visiting our solar system in all of human history. Oumuamua in 2017, the first confirmed interstellar visitor that exhibited its own bizarre anomalies. 2I Borisov in 2019, which behaved much more conventionally like a typical comet. And now 3I Atlas. 3 visitors, 3 data points, and one of them exhibits this extraordinarily rare alignment. That is not a large enough sample size to make definitive statistical claims, but it creates a situation where we must ask uncomfortable questions. Are we simply witnessing selection bias, where only the strangest interstellar objects create enough interesting phenomena to be detected and studied intensively? Are we missing hundreds of boring interstellar rocks that pass through unnoticed because they don't do anything remarkable? Or is there something about interstellar travellers that makes this alignment less rare than geometric probability suggests? Some physical mechanism or some selection effect we do not understand that creates or maintains polar alignments? This alignment contradicts what we previously thought about 3I Atlas based on earlier observations and on standard assumptions about cometary behaviour. Initially, before this detailed motion analysis, researchers assumed the anti-tail was likely a transient feature, perhaps a temporary outburst, possibly a trick of perspective where we happened to be viewing normal tail material from an edge-on angle that made it appear to point sunward when it was actually being blown back, but our viewing geometry created an optical illusion. These are the kind of reasonable assumptions scientists make when confronted with apparently strange observations, looking first for conventional explanations before considering exotic alternatives. But a jet source located at the pole, a feature that sits on the rotation axis rather than somewhere on the body's equator or at random latitude, implies something fundamentally different from transient outburst or perspective effect. It implies stability, permanence, persistence. It implies that this object has been maintaining this orientation, has been keeping one face locked in a specific alignment relative to the solar direction, not through tidal locking, which requires much stronger gravitational fields and much closer approaches than 3I Atlas ever makes, but through this precise rotational configuration where the spin axis tracks the Sun as the object moves along its trajectory. If you're following this analysis carefully, if you're tracking the implications, you will have noticed that as 3I Atlas falls through our solar system, as it moves along its hyperbolic path covering millions of kilometers over months of observation, maintaining pole-sun alignment requires either that the rotation axis is coincidentally aimed in exactly the direction the object happens to be travelling relative to the Sun at this moment, which would be yet another extraordinary coincidence, or that something is actively maintaining or adjusting the orientation as the trajectory curves, as the object's position relative to the Sun changes. For millions of kilometers of travel, through changing gravitational environments, through varying solar heating that should create thermal torques, through outgassing events that should create asymmetric forces perturbing the rotation, this alignment has apparently held. The object has kept one face, one pole, one end of its rotation axis pointed consistently toward the Sun, maintaining configuration that allows the polar jet to continuously direct material sunward rather than spraying randomly, as rotation would carry a non-polar vent through all different orientations. Because of this extraordinary and improbable alignment, because the geometry has settled or been set into this specific configuration, 3i Atlas has established what researchers are calling a stable dayside and nightside despite its distance from the Sun. Let me explain what this means physically, what kind of environmental conditions this creates on the surface of the object, because the thermal implications are profound, and they compound the mystery rather than resolving it. Think about Earth and how our day-night cycle works. We have alternating periods of light and dark because we spin, because our planet rotates on its axis with a period of 24 hours, meaning any given location on the surface cycles between facing the Sun and facing away. If you stand at the equator, you experience roughly 12 hours of daylight when your location is on the sunward hemisphere, followed by 12 hours of darkness when you have rotated to the nighttime side. This creates the daily thermal cycle we are familiar with, heating during day, cooling during night, with the regularity of this cycle driving weather patterns and biological rhythms. Now imagine a completely different scenario, one that does not occur on Earth, but that planetary scientists have studied on other bodies with extreme rotational configurations. Imagine if Earth's North Pole was pointed directly at the Sun, if our rotation axis was oriented perpendicular to the orbital plane rather than tilted at 23.5 degrees. In this configuration, if you lived at the North Pole, the Sun would never set. It would hang in the sky at constant elevation, circling around the horizon but never dipping below it, providing continuous illumination 24 hours per day for 6 months. Meanwhile, if you lived at the South Pole, you would be in complete darkness for that entire 6-month period, eternal night, without any solar heating whatsoever. This is essentially the state that 3i Atlas appears to be maintaining as it travels through space. One pole, one end of the rotation axis, is locked in permanent exposure to solar radiation, baking in continuous heating, receiving energy input that never cycles off because that region never rotates out of view of the Sun. The opposite pole is frozen in permanent shadow, in eternal darkness, shielded from solar heating by the bulk of the object itself, maintaining whatever cryogenic temperature it acquired during millions of years in interstellar space, where the only thermal input comes from the cosmic microwave background and the diffuse glow of integrated starlight. Now you might reasonably ask why this is strange, why this configuration is noteworthy beyond being statistically unlikely. Small bodies throughout our solar system, asteroids and comets and Kuiper belt objects, exhibit many different rotational states. We observe fast rotators that complete spins in hours, slow rotators that take days or weeks, objects that tumble chaotically, binary systems where two bodies orbit each other while both rotate. Surely among all this diversity, pole-on alignments must occur sometimes. And you would be correct that in the vast population of small bodies, geometric diversity means that some fraction will show nearly any configuration you can imagine. But what makes 3i Atlas extraordinary is not just the alignment itself, but the persistence of that alignment combined with the fact that the object is actively outgassing, is producing a powerful jet that is ejecting material with significant momentum, is experiencing forces that should perturb and randomize its rotation state unless something is providing stabilization. Let me explain the physics of why active outgassing usually destroys rotational stability, why jets typically drive comets into chaotic tumbling rather than maintaining clean spin. When material is ejected from a comet's surface, when gas and dust blast outward from a sublimating ice pocket, conservation of momentum demands that the nucleus experiences a reaction force in the opposite direction. It is identical physics to rocket propulsion, where ejecting exhaust backward creates thrust that pushes the vehicle forward. For a comet, ejecting material in any direction creates force that pushes the nucleus in the opposite direction. But here is the critical detail that creates chaos. If a vent is located anywhere off the rotation axis, if it is positioned at some random point on the equator or at intermediate latitude, then the reaction force from outgassing does not pass through the object's center of mass. It creates not just linear force but also torque, rotational force that changes the object's spin rate and can alter its rotation axis orientation. Every outgassing event from an off-axis vent changes the rotation state slightly. Multiple vents in different locations create competing torques. The result is progressive randomization of orientation, tumbling that makes it impossible to maintain any specific alignment with external references like the Sun. Yet 3i Atlas, despite having a jet powerful enough to be detected from Earth across hundreds of millions of kilometres, a jet that must be ejecting significant mass to create the visible anti-tail structure, is not tumbling chaotically. The data shows that as the nucleus rotates with its measured period, the jet precesses in a narrow cone, maintaining tight focus rather than spraying wildly across all angles. The wobble is small, constrained, controlled. Picture a top spinning on a table. As it slows down, as friction drains its angular momentum, the handle begins to trace a circle in the air, a widening cone as the spin axis precesses. That precession is what we observe in 3i Atlas's jet. But the cone is tiny, the deviation from perfect, pulse unalignment minimal. This produces only slight variations in the jet's apparent direction, far less wobble than would be expected if the emission originated from an active region, located at random position on the surface rather than essentially at the pole. If the vent were positioned on the object's equator, if it was offset from the rotation axis by 90 degrees, we would see dramatic effects from what astronomers call the lighthouse effect. As the comet rotates, as the vent sweeps around the axis, the jet would appear to flash on and off, visible when pointing toward Earth, invisible when pointing away. We would see periodic brightness variations with amplitude determined by how the jet's intensity varies with viewing angle. The anti-tail structure would be intermittent, appearing and disappearing with the rotation period. We do not observe that behavior. We see steady emission, continuous presence of the anti-tail, brightness that varies much less than lighthouse effect would create. This implies that the active region producing the jet is positioned such that rotation carries it through only small angular deviations from our line of sight and from the sun direction. It implies location very close to the rotation pole, exactly what the motion analysis has now confirmed quantitatively. This is where the natural explanation, the attempt to understand 3i Atlas through conventional cometary physics, starts to accumulate uncomfortable assumptions and low probability requirements. We must assume that this object, which formed in some distant stellar system unknown billions of years ago, which was ejected into interstellar space through gravitational perturbations or stellar encounters, which travelled for potentially millions of years through the cold dark before happening to pass through our solar system at precisely the moment when humanity has developed technology to detect and study it, just happened to have its largest and most active reservoir of volatile ices located almost exactly at one rotational pole rather than distributed more uniformly or concentrated in equatorial regions or positioned at random latitude. That is one assumption, one requirement that must be satisfied, and we must further assume that this lucky placement of volatiles at the pole combined with another lucky accident of orientation, where the rotation axis just happened to be pointing nearly at the Sun when the object entered our detection range, creating the 0.5% probability alignment we discussed. These are two independent low probability requirements that must both be true simultaneously to explain what we observe through purely natural processes. In scientific investigation, whether we are examining crime scenes or planetary behaviour or any other domain where we attempt to infer causes from observed effects, we start to develop suspicion, we start questioning our assumptions when coincidences stack too high, when multiple independent, low probability requirements must all be satisfied simultaneously. Each individual coincidence might be acceptable, might be within the realm of chance occurrence. But when you need 3 or 4 or 5 lucky accidents all happening together in the same object, the joint probability becomes vanishingly small, even though technically never reaching zero. I want to pause here in our analysis and engage directly with you, with those following this story, because the scientific community is genuinely divided about how to interpret this accumulation of anomalies. Some researchers maintain that we are simply witnessing remarkable, but ultimately natural phenomena, statistical flukes that occur rarely, but inevitably if you observe enough objects. Others are beginning to suggest, usually cautiously and hedged with appropriate skepticism, that perhaps the natural framework is being stretched too far, that perhaps we need to consider alternative hypotheses that might seem radical, but that explain observations more parsimoniously than requiring stacks of coincidences. What do you think based on what we have discussed so far? We are looking at pole-sun alignment with 0.5% probability. We are looking at jet source positioned within 8 degrees of that pole rather than at random location. We are looking at stable orientation maintained over millions of kilometers, despite forces that should randomize rotation. Is this just extraordinary luck? Just the universe rolling low probability dice and getting rare outcomes? Or is there something about interstellar objects, some physics we do not understand, some mechanism that creates or maintains these configurations in ways our current models do not capture? Or are we perhaps looking at something that challenges our comfortable categories, something that might not be purely natural in origin? I genuinely want to hear your perspective. The comment section is not just a place for reactions, it is where this community collectively works through complex problems, where diverse viewpoints and different areas of expertise come together to analyze evidence from multiple angles. Let me know where you stand on the probability spectrum, whether you find the natural explanation convincing, or whether you think we're missing something fundamental. Your input matters because this is not just about one object. It is about how we approach anomalies, how we decide when to revise frameworks, how we balance skepticism against openness to new possibilities. Now let us continue our examination because everything we have discussed so far, the alignment and the stable dayside and the polar jet location, that analysis was based on observations from the inbound leg of 3I Atlas's trajectory, data collected during July and August as the object was falling toward the Sun, approaching perihelion. But orbital mechanics creates an essential asymmetry in trajectories. Objects do not fall straight into stars, they follow curved paths, hyperbolic arcs in the case of interstellar visitors, sweeping around the star and then heading back outward in different direction. As 3I Atlas swung around the Sun, as it executed that perihelion passage on October 29, 2025, the geometry necessarily changed. If the rotation axis remains fixed in space like a gyroscope maintaining orientation relative to distant stars rather than actively tracking the Sun, then the angle between that axis and the Sun direction must change as the object's position along its orbit changes. This is simple geometry, unavoidable consequence of moving along a curved path while maintaining fixed pointing. Think about it using a concrete visualization. If you point your finger at a light bulb mounted on the wall and then walk in a circle around that bulb, eventually your finger is not pointing at the light anymore. Initially your finger aims directly at the bulb. As you circle to the side, your finger starts pointing past it, becoming increasingly misaligned. When you reach the point directly opposite your starting position, your finger is pointing exactly away from the bulb, 180 degrees wrong. Your finger maintained fixed orientation in the room's frame, but that fixed orientation means varying alignment with the target as your position changes. The same geometric logic applies to 3I Atlas. If its rotation axis stays fixed, pointing in a specific direction in space, and if the object moves along its hyperbolic orbit covering large angular distances around the Sun, then the pole-Sun alignment that held during inbound leg should break during outbound leg. The pole that was pointing at the Sun during approach should gradually rotate away from the Sun direction as the object curves past perihelion, until eventually that pole points sideways or even away from the Sun, no longer receiving direct illumination, no longer maintaining the stable dayside condition we discussed. And if the jet source is located at that pole, if the active venting is tied to that specific location, receiving continuous solar heating, then the jet should fade, should weaken, should potentially shut down entirely as that region rotates into shadow, as the thermal input driving sublimation is removed. The antitail should disappear, the anomaly should resolve itself into conventional post-perihelion cometary behavior, where activity declines as objects recede from the Sun and cooling reduces volatile sublimation rates. That is what standard physics predicts. That is what every model of passive rotating bodies following gravitational trajectories demands should occur. The stable dayside phase should end at perihelion. The alignment should break. The jet should fade. And if we observed exactly that sequence, if 3I Atlas had returned to conventional behavior post-perihelion, we would write interesting papers about the remarkable but ultimately transient configuration during inbound leg. We would attribute it to lucky coincidence, and we would move on. But here is the development that has sent researchers scrambling for new explanations, that has transformed curious anomaly into genuine mystery demanding intensive investigation. That is not what happened. As we are about to examine in excruciating detail in our next chapter, the post-perihelion behavior of 3I Atlas does not match predictions from passive rotation models. The jet did not fade, the antitail did not disappear, And the implications of what actually occurred, of how this object adapted to its changing geometry, are forcing serious reconsideration of whether natural frameworks remain adequate for explaining what we are witnessing. We left the previous chapter standing at a critical juncture in our analysis, having established that 3I Atlas exhibited an extraordinarily improbable pole-sun alignment during its inbound approach, a configuration with only 0.5% probability of occurring by chance, creating a stable dayside at one rotational pole that maintained continuous solar heating over millions of kilometers of travel. And we concluded by noting that this alignment, this geometric configuration, should have broken when the object swung around the Sun at perihelion on October 29, 2025, that the curved trajectory should have carried the object into positions where a fixed rotation axis could no longer maintain pole-sun pointing. Now we must confront what actually happened during and after that perihelion passage, because the observational data that has been accumulating from facilities worldwide as 3I Atlas moved through its outbound trajectory phase reveals something that makes the inbound anomaly look almost conventional by comparison. The story does not end with lucky alignment. It continues with behavior that forces us to stack additional low-probability assumptions onto already strained natural explanations, or to seriously consider that we might be witnessing something that operates according to principles we have not encountered before. Let me first establish what we expected to observe, what predictions standard cometary physics makes for objects passing through perihelion and beginning outbound trajectories. We anticipated a transition period, a gradual change as the original pole that was pointed sunward during inbound approach slowly rotated out of direct illumination as the object's position changed. The thermal input to that region should have decreased progressively. The sublimation rate driving the jet should have declined correspondingly. We should have observed the anti-tail weakening, becoming less prominent, potentially fragmenting or dissipating as the driving force diminished, and as solar wind began dispersing the material without continuous replenishment from active outgassing. The brightness of the object should have shown characteristic decline as active regions rotated into shadow, and as the overall volatile production rate decreased, with changing illumination geometry. The periodic variations in brightness that we had been tracking, signatures of rotation carrying differently reflective or differently active regions in and out of view, should have shifted in character as the pole that had been continuously illuminated entered night, and as opposite regions that had been in shadow began receiving sunlight for the first time in the object's recent history. This is not speculative prediction. This is based on well-established physics of how rotating bodies respond to directional heating sources when their orientation changes relative to that source. We have observed this pattern in numerous comets throughout the history of astronomy. Objects brighten as they approach the Sun, and active regions receive increasing solar flux. They reach maximum brightness and maximum activity near perihelion when heating is strongest. Then they fade as they recede, as distances increase and heating decreases, as volatiles in near-surface layers become depleted, and as thermal wave penetration into the interior lags behind the changing external conditions. We waited for this standard pattern to manifest. We prepared instruments to document the expected decline, to measure how quickly the jet faded, to capture the transition from active to relatively dormant state. Multiple observatories coordinated observation schedules to ensure continuous coverage through the critical perihelion period and the immediate post-perihelion weeks, knowing that changes could occur rapidly as geometry and heating conditions shifted dramatically. Instead of observing the predicted decline, instead of documenting conventional post-perihelion fading, what we detected has forced researchers to completely revise their models of what this object is doing and how it maintains its extraordinary behavior across fundamentally different geometric configurations. The images that came back from the Hubble Space Telescope, the data collected by ground-based facilities, the spectroscopic measurements tracking compositional changes and velocity fields, they told a story that contradicts every simple explanation we had constructed. 3I Atlas continues to emit a sharply collimated sunward jet, despite now moving away from the Sun on its outbound trajectory. The anti-tail persists. The beam of material pointing toward our star remains visible, remains coherent, remains tightly focused rather than spreading or dissipating. The feature that should have disappeared, that geometry and thermal physics demanded should have faded as the original active pole rotated into shadow, is still there, still functioning, still producing the anomalous behaviour that first captured attention months ago. Let me emphasise how profoundly this contradicts predictions. The geometry has flipped. The object has swung through 180 degrees of orbital position relative to the Sun. The pole that was continuously heated during inbound approach should now be on the night side, shielded from direct solar radiation by the bulk of the nucleus, cooling rapidly as it radiates away stored thermal energy into the cold of space, without receiving new input from sunlight. That region should be inactive now, frozen, contributing nothing to observed emissions. So how is there still a jet pointing at the Sun? How does the anti-tail persist when the driving mechanism we identified during inbound observations should no longer be functioning? To answer these questions, to explain continued anomalous behaviour using conventional cometry framework, astronomers studying 3I Atlas are forced to invoke what amounts to a second miracle, a second stack of low-probability coincidences that must somehow have manifested in precisely the configuration needed to maintain observations that look almost identical to what we saw during inbound leg despite completely different geometric circumstances. The explanation, the hypothesis that has been tentatively advanced in recent preprints and conference presentations, requires assuming the existence of a second major volatile reservoir on 3I Atlas. Not just a minor secondary deposit, but a substantial ice pocket comparable in size and activity to the first one we identified during July-August observations. And crucially, this second reservoir must be located at a very specific position to explain observed behaviour. It must sit near the opposite rotational pole, at the antipodal point roughly 180 degrees away from the first active region, around the other end of the rotation axis. Think about what this means geometrically. We need two major ice pockets, two substantial deposits of volatile materials capable of driving powerful continuous outgassing, positioned at opposite ends of a small 2-kilometre body, both located within a few degrees of the rotation axis, both essentially at the poles. That is the first requirement, the spatial constraint that must be satisfied for this explanation to work. But the geometric positioning alone is not sufficient. The timing must also be extraordinary, almost perfectly choreographed. This second polar ice pocket, according to the model needed to explain observations, must have been dormant during the entire inbound phase. It could not have been actively outgassing during July and August when we were documenting the first jet. Why not? Because if both poles were active simultaneously, we would have seen symmetrical jets, material being ejected in opposite directions, creating complex dynamics, and possibly cancelling thrust vectors. We did not observe that. We saw a single jet, a clear directed emission from one specific region. So the second deposit had to wait, had to remain inactive while the first pole received continuous illumination, and while that region drove the jets we observed and analysed. And then, as the object swung through perihelion, as the geometric configuration flipped and the original active pole rotated into shadow, this second previously dormant deposit had to activate at precisely the right moment, had to begin outgassing with sufficient intensity to maintain the anti-tail feature, had to produce emission characteristics matching what we had been observing from the first pole closely enough that the overall appearance of the object remained consistent. It is a perfect handoff, a seamless transition where one engine shuts down and a second engine starts up in synchronized sequence, maintaining overall system behavior despite swapping which specific component is providing the driving force. Pole A drives the jet on the way in, producing continuous sunward emission for months. Then at perihelion, as geometric alignment breaks for Pole A, Pole B takes over, producing essentially identical behavior but from the opposite side of the object, maintaining the anti-tail and maintaining the pole-sun alignment that geometry should have destroyed. Let us examine the probability of this occurring naturally, of all these requirements being satisfied simultaneously through pure chance rather than through any organising principle or active control. We start with the original 0.5% probability for the first pole-sun alignment, the unlikely but not impossible geometric configuration during inbound approach. That is our baseline, the first low probability requirement. Now we must add a second active region positioned at the opposite pole, within similar angular tolerance of 8 degrees from the rotation axis. The probability of having a second major volatile deposit located in that specific narrow region, given that ice pockets on comets are generally distributed more or less randomly, or concentrated in equatorial regions where impacts might have deposited material, or where structural weaknesses allow venting, is again on the order of that same 0.5%. It is another 1 in 200 shot. But these probabilities are not independent. We need both conditions to be true simultaneously. We need the first pole to have its ice pocket and appropriate alignment, and we need the second pole to have its ice pocket and appropriate positioning. When you combine independent probabilities, when you require multiple low probability events to all occur together, you multiply the individual probabilities. 0.5% times 0.5% equals 0.025%. That is 1 in 40,000. That is the joint probability of having two antipodal polar ice deposits, both positioned within the narrow angular zones, required to explain the switching jet behavior through natural geometric coincidence. We have moved from unlikely to statistically absurd, from rare event that happens occasionally to extreme outlier that should essentially never occur in the limited sample of interstellar visitors we have observed or expect to observe in coming decades. And we have not even yet accounted for the timing requirement, the fact that the second pole had to remain dormant during inbound leg and then activate at exactly the right moment during perihelion passage to maintain continuity of jet behavior. If both poles were simply exposed ice that responded directly to solar heating, both should have been active whenever receiving illumination. The fact that we see sequential activation rather than simultaneous operation suggests either that the second deposit was covered by insulating material that only got removed at perihelion, which would be yet another coincidence, or that the triggering mechanism for activation involves something more complex than simple thermal response to sunlight. Let me provide a concrete analogy to make this probability assessment more intuitive, more connected to experience, where we can evaluate how reasonable it is to invoke such rare combinations of coincidences. Imagine you are investigating a spacecraft, a human-designed vehicle built with specific purposes and engineered systems. You notice it has a main thruster on the forward end that fires during approach to a planet, providing deceleration to slow down and match orbital velocity. Then, as the spacecraft swings around the planet using gravity assist, as it begins departing on the outbound leg of its trajectory, that forward thruster shuts off and a rear thruster activates, providing acceleration to boost velocity as it leaves. That behavior looks like a controlled maneuver, like intelligent design implementing a specific mission profile. It looks like engineering. Now imagine instead you're examining a natural asteroid, a dumb rock tumbling through space, and you observe what appears to be the same pattern. It has a thermal vent on one end that releases gas during inbound approach, creating thrust effects. Then at closest approach to the Sun, that vent shuts down, and a second vent on the opposite end activates, producing similar thrust during outbound departure. You can explain this through natural processes. You can construct a scenario involving two separate ice pockets, specific thermal properties, precisely timed triggering, all occurring through coincidence. But as you stack the requirements, as you list all the things that must happen just right for the natural explanation to work, you start to wonder whether the simple explanation, the one that makes all the pieces fit without requiring luck, might actually be that you are looking at something that was designed, something that exhibits these characteristics, because they serve functional purposes rather than because random chance happened to configure materials in exactly this improbable arrangement. This is the philosophical tension at the heart of the 3i Atlas debate, playing out in research groups and in preprint comment sections and in hallway conversations at conferences. The natural explanation is technically possible. Nothing violates known physics. All the required elements could in principle occur through stochastic processes, through the grinding operation of basic chemistry and thermodynamics operating over billions of years of solar system formation and evolution in whatever distant stellar system gave birth to this object. But the explanation requires accepting that we have witnessed extraordinarily unlikely configurations, that we are looking at an extreme statistical outlier, that the universe rolled multiple low-probability dice and got rare outcomes on all of them simultaneously. The alternative explanation, the one that makes some researchers deeply uncomfortable because of the implications, is that the behavior looks engineered because it is engineered, that we are observing characteristics that serve functional purposes because they were designed to serve those purposes, that the pole-sun alignment and the switching jets and the maintained anti-tail are features rather than bugs, intentional properties of a system built to operate in specific ways rather than accidents of natural configuration. I want to be very clear about something important before we go further into analysis. I'm not claiming that 3i Atlas is definitely artificial. I am not asserting that we have proven it is a probe or a spacecraft or a manufactured object. The evidence does not support definitive conclusions yet. What I am arguing is that the natural explanation has become sufficiently strained, sufficiently dependent on multiple compounding improbabilities, that we should take the artificial hypothesis seriously as a possibility worth investigating, rather than dismissing it reflexively as too exotic to merit consideration. Science appropriately maintains high skepticism for extraordinary claims. The burden of proof for asserting artificial origin is heavy, as it should be, because such claims carry profound implications about galactic civilization prevalence and technological capabilities and contact scenarios. But scientific skepticism should not become rigid dogmatism that refuses to examine evidence because conclusions might challenge comfortable assumptions. When observations accumulate that strain natural frameworks, when we find ourselves invoking epicycles upon epicycles to preserve existing models, intellectual honesty demands we at least explore whether alternative frameworks might explain data more parsimoniously. And here is where the story takes another turn, where additional observations compound the mystery rather than resolving it. The transition at perihelion, the switching between poles that we have been discussing, was not gradual or rough or characterized by instability and fluctuation, as you might expect from natural processes responding to changing thermal conditions. The data from Hubble Space Telescope, from ground-based facilities tracking the object through perihelion passage, show something remarkable and troubling. The transition was seamless. The light curve, the plot of brightness versus time that we use to track overall activity level and to detect variations that reveal rotation and changes in outgassing, remained smooth through perihelion. There was no dip, no period where both poles were inactive, simultaneously causing brightness to fall, no spike where both might have been briefly active together, causing brightness to surge. The handoff from one pole to the other occurred with continuity that suggests near-perfect coordination. If this were a natural thermal process, if we were simply observing passive response to changing illumination, as rotation carried different regions into and out of sunlight, we would expect lag effects. Heat does not instantly penetrate into a comet nucleus when sunlight hits the surface. Thermal conduction is slow, measured in hours to days depending on material properties and depth of volatile reservoirs. When a previously shadowed region rotates into sunlight, it takes time for the temperature to rise through the tens or hundreds of Kelvin needed to drive significant sublimation. There should be a warm-up period, a gradual increase in activity rather than instantaneous turn-on. Similarly, when an active region rotates into shadow, cooling is not instantaneous. Thermal inertia means the heated material retains elevated temperature for some time, continuing to outgas even after solar input ceases, with activity trailing off gradually rather than shutting down immediately. The combination of these lag effects should produce a transition period where the first pole is winding down while the second pole is ramping up, creating overlap or gap depending on specific timing and thermal properties. But the observations show neither significant overlap nor gap. The transition appears almost instantaneous relative to the timescales involved. This suggests that the material on 3I Atlas, particularly whatever volatiles are driving the jet activity, is extraordinarily sensitive to solar radiation, far more reactive than typical cometary ices that we have studied in our own solar system's comet population. The surface must be either very dark, absorbing solar energy efficiently, or the crust must be extremely thin, allowing heat to quickly reach subsurface volatiles, or the volatile species themselves must be supervolatiles that sublimate at very low temperatures, far below the roughly 200 Kelvin where water ice becomes highly active. Some researchers have proposed that 3I Atlas might be rich in carbon monoxide ice, or nitrogen ice, species that remain frozen only at temperatures below about 25 Kelvin for CO, and 63 Kelvin for N2, far colder than the approximately 170 Kelvin where carbon dioxide ice sublimates significantly, and the 180 Kelvin water ice threshold. Supervolatiles like these would be much more sensitive to small temperature changes, would respond almost immediately to solar illumination, and would explain the rapid activation we observe. But supervolatile composition creates its own puzzles. These ices are so easily sublimated that they should have been lost long ago during the object's history. If 3I Atlas spent billions of years in interstellar space at temperatures of just a few Kelvin, supervolatile ices could be preserved in that deep freeze. But the object also spent time in its origin stellar system, presumably orbiting close enough to its parent star to receive the heating that we discussed earlier as explaining the thermally processed appearance and composition. That heating should have driven off any supervolatiles present, leaving only the more refractory species like water and CO2 that require higher temperatures to sublimate significantly. To preserve supervolatiles through thermal processing in the origin system, we would need to assume they are buried deep beneath insulating layers, protected from surface heating, only recently exposed by fracturing or erosion or some other process that breached the crust. But then how do we explain that these deeply buried reserves are positioned precisely at both rotational poles? How did the object happen to fracture or erode in exactly the narrow regions needed to expose polar deposits on both ends simultaneously? More coincidences, more low probability requirements stacking up. The symmetry problem continues to dominate attempts at natural explanation. The emerging picture from data and from models attempting to fit observations is of an object that is almost perfectly balanced, with two major structural features positioned at opposite ends, both oriented along the rotation axis, both exhibiting similar properties and similar activity levels. Natural bodies, bodies formed through stochastic accretion of smaller particles or through collision and gravitational aggregation, do not generally produce such symmetry. They are lumpy, irregular, heterogeneous, reflecting the random nature of their formation and evolution. Yes, some objects show binary character, two similarly sized lobes joined by narrow neck, formed presumably through gentle collision and merger of separate bodies. But even contact binaries generally show a symmetry between the lobes, differences in composition or structure or rotation state. Finding a small object like 3I Atlas exhibiting this degree of symmetry in its volatile distribution and activity pattern is like finding a perfectly spherical boulder on a rocky beach, technically possible through chance erosion, but so unlikely that you would seriously consider alternative explanations, including that someone shaped it intentionally. Now we arrive at a critical question that will determine how we interpret all of this evidence, how we weigh the competing hypotheses, how we decide what conclusions are justified by observations. What is the appropriate baseline probability, the prior expectation, that we should assign to artificial versus natural origin for interstellar visitors? This question is not just philosophical abstraction. It directly impacts how much evidential weight is needed to shift conclusions from one hypothesis to another. If you start with the assumption that artificial interstellar probes are vanishingly rare, that the probability of any given interstellar object being manufactured rather than natural is 1 in a million or 1 in a billion, then even quite strong evidence accumulating multiple anomalies might not be sufficient to overcome that strong prior and make artificial origin seem likely. You would need smoking gun evidence, completely unambiguous signatures like detection of regular geometric structure or radio transmissions or visible mechanical components, before you would accept artificial explanation. But if you start with a more agnostic prior, if you allow that perhaps technological civilizations are not vanishingly rare in the galaxy, and that those which exist might have motivations to send probes to other stellar systems, and that detection of such probes when they pass through our system is not impossibly unlikely, given improving astronomical capabilities, then the evidential bar is lower. Accumulating multiple unexplained anomalies, seeing behavior that looks functionally aligned with what probes would do, even without smoking gun signatures, might be sufficient to make artificial hypothesis competitive with or even preferable to strained natural explanations. Different researchers, different analysts examining the same data, reach different conclusions largely because they are operating from different priors, different baseline assumptions about what is probable versus improbable in the universe. And there is no objective way to set these priors because we lack data on the prevalence of interstellar probes, lack comprehensive surveys of what technological civilizations do or don't do, lack understanding of whether panspermia seeding missions or exploration programs or communications networks or whatever other purposes might motivate interstellar probe deployment are common or rare. What we can do is be honest about uncertainty, about the fact that multiple frameworks remain consistent with observations, even if they require different combinations of assumptions. We can continue gathering data, continue refining measurements, continue looking for observations that might discriminate between competing hypotheses, and we can remain open to possibility that our comfortable categories, our binary classification of objects as natural versus artificial, might not capture the full reality of what exists in a galaxy far more complex than our limited experience prepares us to comprehend. As we prepare to move to the next chapter of our analysis, as we shift focus from timing and geometry to the physical properties of the jet itself, I want to leave you with the probability numbers clear in mind. 0.5% chance for initial alignment, another 0.5% for second polar deposit. Combined probability of 0.025%, 1 in 40,000, for having both conditions necessary to explain switching jet behavior through natural coincidence. And we have not yet addressed the seamless transition timing, the symmetry of the configuration, the super volatile composition requirements, all of which add additional low probability constraints. In the next segment, we will examine the strangest property of all, the characteristic that has physicists most puzzled. We will look at the jet itself, at how this beam of material is behaving as it extends from the nucleus toward the sun across distances that dwarf the scale of the object itself. Because what we observe there, what the high-resolution imaging reveals about how this jet maintains cohesion and directionality, defies standard models of how gas and dust should behave in the vacuum of space under the influence of solar radiation and solar wind. The columnation puzzle awaits, and it will force us to question even more fundamental assumptions about what we think we understand. We have established that 3I Atlas exhibits extraordinarily improbable geometric alignment during inbound approach, with 1 in 200 odds, and that it somehow managed to maintain anomalous jet behavior through perihelion by apparently activating a second antipodal polar deposit in perfect synchronization, compounding probabilities to 1 in 40,000. These timing and geometric mysteries are profound, but they remain at least theoretically explicable through stacked natural coincidences, even if the required assumptions strain credulity. Now we must turn our attention to a different category of anomaly, one that challenges not just probability, but fundamental physics, that forces us to question whether standard models of how matter behaves in space adequately describe what we are observing. The December 15th observations, captured just 2 days ago, as this object continues its approach toward closest passage to Earth, reveal a structure in space that should not exist according to conventional understanding of gas dynamics and particle physics. The images that came back from multiple facilities, independently confirming the phenomenon through different instruments and different analysis techniques, show the anti-tail of 3I Atlas remaining tightly collimated over a distance exceeding 500,000 kilometers. Let me repeat that number because its significance cannot be overstated. 500,000 kilometers, 500,000 kilometers. A beam of material extending from a nucleus perhaps 2 kilometers in diameter, across a span 250,000 times larger than the source object. To put this extraordinary distance in perspective, in a way that connects to scales we can more intuitively grasp, the distance from Earth to the Moon averages about 384,000 kilometers. The lunar orbit, that fundamental distance that defines our nearest celestial neighbor, that represents the frontier humanity has physically crossed with our Apollo missions, fits entirely inside the length of this jet with room to spare. If you positioned Earth at one end of this beam and started traveling along, its length at the speed of light, it would take 1.67 seconds to reach the other end, covering distance that light traverses in time you can count on your fingers. And throughout this entire enormous span, the jet maintains coherence. It does not fan out into the broad diffuse cloud that physics demands should form when gas expands into vacuum from a localized source. It does not get torn apart by solar wind, the continuous stream of charged particles flowing outward from the sun at velocities around 400 kilometers per second, carrying magnetic fields that interact with and push against ionized material. It does not spread significantly under radiation pressure, the physical momentum carried by photons from the sun that exerts force on any illuminated surface or particle. Imagine for comparison a flashlight beam cutting through fog. At the source, where the bulb emits light, the beam emerges from a small aperture perhaps a few centimeters across. But as the beam travels, as light propagates away from source, it spreads. Divergence is inevitable consequence of emission from finite-sized source, of slight misalignments in the optical system, of diffraction effects at beam edges. By the time this flashlight beam has travelled 100 feet, it might illuminate a circle several feet in diameter on a wall, The light spread over a much larger area than the originating aperture, intensity diminished accordingly. Now imagine instead a laser pointer. The beam emerges from a small source and propagates with minimal divergence, maintaining tight focus over enormous distances compared to source size. A quality laser pointer can put a tight spot on a wall hundreds of meters away, can even be visible reflecting off the moon when used by observatories, maintaining beam coherence across 384,000 kilometers of empty space. But laser beams achieve this extraordinary collimation through a specific physical mechanism, through stimulated emission creating photons that are coherent in phase and direction, through careful optical design using mirrors and lenses to shape wavefronts. The jet from 3I Atlas is not made of photons. It is composed of matter, of gas molecules and dust particles that have mass and that obey different physics than light. And it is behaving more like a laser than like a flashlight, maintaining focus that defies our understanding of how material jets should propagate through space. This is the collimation puzzle, and it represents perhaps the most physically troubling aspect of the entire 3I Atlas mystery, because it cannot be explained away through improbable coincidence or lucky geometry. This requires physics we do not understand or mechanisms we have not identified operating on this object. Let me explain what we mean by collimation and why lack of spreading is so problematic for natural explanations. When gas escapes from a solid surface into vacuum, when molecules that were bound in ice or absorbed in regolith get released through sublimation or heating and transition from condensed phase to free gas, they carry thermal energy with them. This thermal energy manifests as random molecular motion, as molecules moving in all directions with velocities determined by temperature through standard kinetic theory. Higher temperature means higher average velocities, with Maxwell-Boltzmann distribution describing the range of speeds you expect to find in the gas. Even if gas emerges from a small vent or crack, even if the source region is highly localized, the random thermal velocities of molecules mean that the gas expands in all directions as it leaves the surface. There is a net flow direction, a bulk velocity component in the direction perpendicular to the surface at the vent location, but superimposed on this directed flow is random thermal motion, causing molecules to spread laterally as they travel. This spreading is fundamental, unavoidable consequence of finite temperature. The only way to have zero divergence would be temperature of absolute zero, where all thermal motion stops, which is physically impossible to achieve and certainly not expected in a comet coma, where temperatures are hundreds of Kelvin. Standard gas dynamics calculations show that material ejected from a small source at typical cometary outgassing velocities, perhaps 0.5 to 1 km per second, for water vapor sublimating from ice at temperatures around 200 Kelvin, should expand into a cone with opening angle determined by the ratio of thermal velocity to bulk flow velocity. For reasonable parameters, this cone might have half angle of 10 to 30 degrees, meaning that after travelling 500,000 kilometres, material initially emitted from a 2-kilometre source should be spread over a region tens of thousands of kilometres across, creating a diffuse cloud rather than a tight beam. But that is just the expansion from thermal motion, just the intrinsic divergence you get from finite temperature. On top of that basic gas dynamics, we must account for external forces acting on the material once it has left the nucleus and entered the space environment. Solar radiation pressure exerts force on any particle illuminated by sunlight, force that scales with the particle's cross-sectional area, but must accelerate the particle's mass. For small particles, for dust grains measured in micrometers, the area-to-mass ratio is high, and radiation pressure is extremely effective at pushing particles away from the sun, accelerating them to velocities that can exceed the bulk gas flow velocity. This is why normal comets have dust tails that point away from the sun, broad fan-shaped structures where small particles have been blown back by radiation pressure and spread over large angular regions as they travel away from the nucleus. The smallest particles get pushed hardest, travel fastest, spread widest. Larger particles respond less to radiation pressure, but still experience force that should disrupt tight collimation. Even if initial ejection is highly directional, radiation pressure should destroy that directionality over large distances, spreading material perpendicular to the radial direction and preventing maintenance of narrow beams. Solar wind provides additional disruptive force. This continuous flow of charged particles from the sun, mostly protons and electrons streaming outward at hundreds of kilometers per second, carries embedded magnetic fields that interact electromagnetically with ionized particles in cometary comae. When gas molecules get ionized by solar UV radiation, as many molecules do in the intense radiation environment close to the Sun, they become susceptible to magnetic forces. The solar wind magnetic field lines, which are draped around the Sun and carried outward by the wind flow, can trap ionized particles and carry them away from the comet, again acting to spread and disperse material rather than allowing it to maintain coherent beam structure. Given all these spreading mechanisms, given the multiple physical processes that should destroy collimation, the fact that 3I Atlas's anti-tail maintains tight focus over 500,000 kilometers is deeply puzzling and demands explanation. There are only a few ways that material jets can maintain coherence over such distances in space environments, and examining these possibilities reveals how exotic the conditions or mechanisms must be to explain what we observe. Possibility 1. The material is being ejected at extraordinarily high velocity, so fast that it covers the 500,000 kilometer span before having time to spread significantly under thermal motion or external forces. For this to work, for this to overcome the spreading mechanisms we discussed, ejection velocity would need to be on the order of hundreds of kilometers per second, or even approaching thousands of kilometers per second. These are not the gentle velocities of sublimating ice. These are velocities comparable to or exceeding escape velocity from massive planetary bodies, velocities that require enormous energy input. To give concrete comparison, escape velocity from Earth's surface is about 11 kilometers per second. Gas molecules sublimating from ice at temperatures around 200 Kelvin have thermal velocities on order of 0.5 kilometers per second. To accelerate material from cometary ice to hundreds of kilometers per second requires either temperatures of tens of thousands of Kelvin, which is completely incompatible with the icy composition and the thermal balance calculations for objects at 1-2 AU from the Sun, or it requires some other acceleration mechanism beyond simple thermal expansion, some process that can add energy to particles after initial ejection. One possibility that has been discussed in theoretical papers is electrostatic acceleration, where surface charging creates electric fields that can accelerate ionized particles to high velocities. If a comet nucleus becomes electrically charged through interaction with solar wind or through emission of photoelectrons when UV photons strike the surface, potential differences of hundreds or thousands of volts could develop. Ions leaving the surface would be accelerated by these electric fields, potentially reaching velocities far exceeding thermal speeds. But electrostatic acceleration requires sustained charging, requires some mechanism to maintain voltage differences against discharge processes that tend to neutralize charge buildup. It requires that significant fraction of ejected material be ionized rather than neutral, because neutral molecules do not respond to electric fields, and it requires explaining why we do not see clear spectroscopic signatures of the high-energy ions that such acceleration would produce, why the emission lines we observe do not show the Doppler broadening and shifted wavelengths characteristic of particles moving at hundreds of kilometers per second. Possibility 2. The particles in the jet are much heavier than typical cometary dust, massive enough that their high inertia makes them largely immune to radiation pressure and solar wind forces. If the jet consists primarily of pebbles or even larger rocks rather than fine dust grains, if we are looking at a stream of centimeter scale or larger objects, they would maintain their initial velocity vectors much better than small particles, would be less deflected by external forces, would in principle be capable of forming relatively narrow beams if ejection was sufficiently directional. But heavy particles create their own puzzles. How does a small comet nucleus, an object only 2 kilometers across with surface gravity, measured in millimeters per second squared, generate enough energy to eject rocks at escape velocity and beyond? Sublimation pressure from ice turning to gas can loft fine dust and can accelerate small particles to modest velocities, but launching substantial rocks requires much more energetic processes. You need explosive events, sudden pressure releases from subsurface voids, perhaps impacts or structural collapses or other catastrophic mechanisms that do not naturally explain continuous steady jet emission over months of observation. And if the jet is heavy particles, where is the gas? Every comet we have studied shows substantial gas emission, not just dust. The spectroscopic observations of 3I Atlas clearly detect molecular emission lines, indicating the presence of volatiles being released water and carbon dioxide and various organic species. A purely particulate jet made of heavy rocks would not produce the molecular signatures we observe. We need both gas and heavy particles coexisting in the jet, maintaining coherence together despite their very different responses to external forces, and we need to explain how this mixed-phase jet maintains collimation when normal comet tails show complete separation between gas and dust components due to their different dynamics. Possibility 3, and this is, where we venture into truly exotic territory, into mechanisms that conventional comet physics does not include. The jet is somehow magnetically confined. If there is a magnetic field involved, if the flowing material is ionized and therefore responds to magnetic forces, it is theoretically possible to create configurations where magnetic field lines funnel particles into narrow beams, preventing lateral spreading through magnetic pressure that opposes expansion perpendicular to field direction. This is how astrophysical jets from active galactic nuclei and from young stellar objects maintain collimation over enormous distances. The jets from supermassive black holes can extend for millions of light years while remaining relatively narrow, focused by magnetic fields that are amplified and organized by rotating accretion disks. Pulsars emit jets of relativistic particles confined by the neutron star's intense magnetic field, creating tightly beamed radiation that sweeps across the sky like a lighthouse. But comets do not have strong magnetic fields. Small icy bodies lack the internal dynamo mechanisms that generate planetary magnetic fields, lack the conducting cores and rapid rotation needed to produce significant magnetism. Some asteroids show weak remnant magnetization in their rocks, fossil fields frozen in from early solar system conditions, but these remnant fields are far too weak to confine gas jets. To achieve confinement strong enough to prevent spreading over 500,000 kilometers would require field strengths measured in Gauss or even Tesla, intensities comparable to laboratory electromagnets or to compact astrophysical objects like neutron stars. Where would such a field come from on a 2-kilometer icy body? If 3I Atlas is purely natural, there is no plausible source for the required magnetic field strength. But if we allow ourselves to speculate about artificial origin, if we consider that this might be a manufactured object rather than a natural comet, then magnetic confinement becomes at least conceivable. A technological probe could potentially carry superconducting coils or permanent magnets capable of generating substantial fields, could use these fields to shape and direct exhaust from propulsion systems, or to organize emissions from surface features for scientific or functional purposes. I want to emphasize that we have no direct evidence for magnetic fields on 3I Atlas. We have not detected them spectroscopically, have not observed polarization in emitted light that would indicate organized magnetic structure. The magnetic confinement hypothesis is speculation motivated by trying to explain otherwise inexplicable collimation, not by positive detection of the mechanism itself. But the fact that we are driven to speculate about such exotic mechanisms that have no precedent in normal cometary behavior, illustrates how profoundly the observations challenge standard frameworks. The upcoming spectroscopic observations, the detailed measurements scheduled to occur during the December 19th closest approach window now less than 48 hours away, will provide critical constraints on jet properties that may allow us to discriminate between these competing possibilities. Spectrographs will measure the composition of material in the jet, determining whether it is primarily gas or contains significant dust component, whether molecular abundance ratios match typical cometary values, or show anomalous enrichments or depletions that might indicate exotic processes. More crucially, spectroscopy will measure velocities through Doppler shift. When molecules or atoms move toward or away from observer, the wavelengths of their emission lines shift slightly toward blue if approaching, or toward red if receding. The magnitude of shift depends on velocity component along line of sight. By measuring these shifts precisely, by mapping how different parts of the jet show different Doppler velocities, we can determine the three-dimensional velocity field, can see whether material is moving at the modest speeds, typical of cometary outgassing, or at the much higher velocities that would be required for kinematic collimation through speed alone. If we find that the jet material is moving at many hundreds of kilometers per second, if velocities dramatically exceed what thermal sublimation can produce, that would be definitive evidence for some energetic acceleration mechanism operating beyond simple gas expansion. We would be forced to identify what physics can add so much kinetic energy to particles. What could be driving such extreme conditions in material ejected from what appears to be a cold, icy body? If instead we find normal cometary velocities, modest speeds on order of kilometers per second, then we are left with the collimation puzzle in its full mystery, because slow-moving material should spread over such large distances, should not maintain the tight beam we observe. We would need to invoke confinement mechanisms, either magnetic as discussed, or possibly something even more exotic like electrostatic focusing, or radiation pressure balance in some special configuration, or potentially mechanisms we have not yet conceived. The spectroscopy will also reveal ionization state of the gas. If substantial fraction of molecules in the jet are ionized, if we detect strong ion emission lines alongside neutral molecular emission, that would support hypotheses involving electrostatic acceleration or magnetic confinement, since these mechanisms require charged particles to operate. If the jet is primarily neutral molecules, then electromagnetic mechanisms become implausible, and we are forced back to trying to explain collimation through purely hydrodynamic or kinematic means. Beyond the gross physical properties of velocity and composition and ionization, the spectroscopy may reveal more subtle clues about conditions at the source. Temperature can be inferred from line widths, from the Doppler broadening caused by random thermal motion of emitting atoms or molecules. Anomalously high or low temperatures would constrain what processes are occurring. Excitation states, which molecules are excited to higher energy levels versus ground state, tell us about radiation field intensity and about collisional environment, about whether gas is dense enough for molecules to collide frequently, or tenuous enough that each molecule propagates essentially independently. All of this data, all these measurements that will flood in from observatories worldwide during the critical approach window, will help constrain the physics of the jet, and potentially allow us to eliminate some hypotheses while supporting others. But here is what concerns me. What keeps trajectory specialists and theorists debating late into night as this object approaches. Even with better data, even with definitive measurements of velocities and compositions and temperatures, we may find ourselves in a situation where no conventional mechanism adequately explains all the observations simultaneously. We may determine that velocities are too low for kinematic collimation, yet find no evidence for the strong magnetic fields that confinement would require. We may see ionization levels that are insufficient for electrostatic acceleration, yet observe collimation that demands some focusing mechanism beyond just fortunate initial directionality. We may measure temperatures and densities that are completely normal for comet comae, yet be confronted with jet behavior that normal comae do not produce. This is the position researchers increasingly find themselves in, as each new observation adds detail, but does not resolve fundamental questions, as we accumulate more precise data about anomalous behavior without identifying physical mechanisms that can explain why the anomalies occur. And there is one final piece of evidence we must examine, one additional clue that compounds the mystery and that connects back to the alignment and switching phenomena we discussed in earlier chapters. The jet wobble, the periodic variation in jet pointing direction that allowed researchers to locate source within 8 degrees of rotation pole, provides information not just about source location, but about rotation rate of the nucleus itself. By measuring how fast the wobble period is, how long it takes for the jet to complete one full precession cycle, we can determine how rapidly the object is spinning. The data indicates a rotation period of approximately 15.5 hours. This is the time required for one complete rotation, for the nucleus to spin once around its axis. At 15.5 hours with a nucleus diameter of about 2 kilometers, we can calculate the rotational velocity at the equator, the linear speed with which surface features are moving due to spin. The result is roughly 0.1 meters per second, about the speed of a slow walk, far below velocities that would create significant centrifugal forces on surface materials. Why does rotation rate matter? Because it tells us about mechanical forces, about whether rotation itself could be responsible for ejecting material or for maintaining jet activity through centrifugal stresses. For objects spinning very rapidly, for rotation periods of just hours or even minutes, when the body's only kilometers across, centrifugal acceleration at the equator can become substantial, can approach or even exceed surface gravity. In such cases, material is literally flung off the surface by rotation, and jets can be mechanically driven rather than requiring thermal sublimation. But 15.5 hours is slow rotation, leisurely spin that creates negligible centrifugal effects. The centrifugal acceleration at 3I Atlas's equator is a tiny fraction of even the weak surface gravity, completely inadequate to explain mass ejection through mechanical means. This tells us definitively that the activity we observe, the powerful jet producing the collimated beam and the anti-tail structure, cannot be attributed to rotation trying to tear the object apart, or to centrifugal forces helping to launch material. The energy driving jet formation is purely thermal or internal, arising from sublimation heating or from subsurface pressure, or from whatever mechanism is mobilizing volatiles, not from mechanical stresses imposed by rotation. Slow rotation also has implications for stability and orientation maintenance. Objects spinning rapidly have substantial rotational angular momentum, which provides gyroscopic stability resisting perturbations that try to change spin axis direction. But slowly rotating objects lack this stabilization. They should be more susceptible to tumbling, to having their orientation altered by external torques, from asymmetric outgassing, or from tidal effects, or from impacts with dust grains. The fact that 3I Atlas maintains stable orientation despite slow rotation, despite having weak gyroscopic resistance to perturbation, is yet another piece of the puzzle, suggesting that something beyond passive dynamics is operating. As we synthesize all of these observations, as we attempt to build coherent picture from the accumulating evidence, we face profound tension between data and theory. We see an object that maintains pole-sun alignment with improbable geometry, that switches active regions with impossibly good timing, that produces a jet-maintaining collimation that defies gas dynamics, and that does all of this while rotating too slowly for mechanical forces to explain activity, or for gyroscopic stability to explain orientation maintenance. Each individual anomaly strains natural explanation. Collectively, they create a pattern that is becoming increasingly difficult to fit into conventional frameworks without invoking long chains of special circumstances and low probability configurations. Now, as we stand less than 48 hours from closest approach, as observatories worldwide prepare their instruments and coordinate observation schedules and wait for this enigmatic visitor to pass through the optimal viewing window, we must ask what outcomes from those observations would definitively resolve the mystery versus what results would simply deepen the questions. In our final chapter, we will examine the technological hypothesis directly. We'll explore what characteristics we would expect to see if 3I Atlas is artificial rather than natural. We'll discuss how the December 19th data might allow us to discriminate between these possibilities, and we'll confront the implications of each scenario for our understanding of what travels between the stars and what that tells us about whether we are alone in the galaxy or whether intelligence and technology are common features of cosmic evolution. We have walked through the evidence systematically, examining each anomaly in detail, calculating probabilities, exploring physical mechanisms, and repeatedly finding that natural explanations require stacking improbable coincidences or invoking exotic processes that have no precedent in normal cometary behavior. The pole-sun alignment with 0.5% probability, the antipodal switching with combined odds of 1 in 40,000, the collimated jet that defies gas dynamics and maintains coherence over 500,000 kilometers through mechanisms we cannot identify, the stable orientation despite slow rotation that should make the object susceptible to tumbling. Now we must confront directly the hypothesis that most researchers are reluctant to discuss in formal publications, but that increasingly dominates private conversations and email exchanges and late-night discussions at conferences. Is 3I Atlas artificial? Before we explore what technological origin would mean, what characteristics we should expect if this is a probe rather than a natural comet, I want to establish a clear framework for how we should approach this question scientifically. The artificial hypothesis is not inherently unscientific, despite the profound implications it carries. It is testable through observations, makes specific predictions that can be compared against data, and can be evaluated using standard evidential reasoning just like any other hypothesis in astronomy or planetary science. The fact that conclusions might be unsettling, might challenge our assumptions about humanity's uniqueness, or about the prevalence of intelligence in the galaxy, does not make the question illegitimate or place it outside the domain of serious investigation. What makes a hypothesis scientific is not whether it sounds conventional or whether it aligns with existing theories, but whether it explains observations, makes falsifiable predictions, and can be tested empirically. By these criteria, The technological hypothesis for 3i Atlas is entirely within bounds of legitimate scientific inquiry. We can ask what characteristics an interstellar probe would exhibit, can compare those predicted characteristics against what we actually observe, can identify what additional observations would strengthen or weaken the hypothesis, and can maintain appropriate skepticism while following evidence honestly wherever it leads. So let us conduct that analysis rigorously. If we assume, for the sake of argument, that 3i Atlas is not a natural comet, but is instead a manufactured object, an artifact of technological civilization from some other stellar system, what functional characteristics would we expect it to display? What design features would be logical for an interstellar probe, given the constraints of physics and the probable goals that would motivate sending such an object across light years of space? First and most fundamental, thermal management and orientation control would be critical for any probe designed to operate in the varying thermal environments encountered when approaching and receding from stars. As the probe falls toward the Sun, as solar heating intensifies by inverse square law with decreasing distance, internal components must be protected from overheating that could damage sensitive instruments or cause structural failures. The most straightforward protection mechanism is a heat shield, a surface designed to absorb or reflect solar radiation while maintaining safe temperatures on the protected side. But a heat shield is only effective if it remains oriented correctly, if the protective surface faces the Sun continuously, rather than tumbling randomly and allowing unprotected regions to bake in direct sunlight. This requires active orientation control or at minimum passive stability that maintains sun-pointing attitude. The pole-sun alignment we observe in 3i Atlas, the configuration where rotation axis points directly at the star, is exactly the orientation a heat-shielded probe would maintain. It allows one end to serve as thermal protection while keeping the rest of the body in shadow, creating the stable day-side-night-side division we discussed earlier as an anomalous feature for natural comets, but entirely expected characteristic for spacecraft with thermal constraints. The switching behavior at perihelion, that mysterious activation of the opposite pole as the object swung around the Sun, makes perfect sense in thermal management context. During inbound approach, one end of the probe faces the Sun, experiences maximum heating, and must dissipate or reflect that energy to prevent damage. At perihelion, as the trajectory curves and the probe's position relative to the Sun changes by 180 degrees, maintaining sun-pointing attitude requires the opposite end to now face the star. The switching we observe might simply be thermal response as first one end and then the other, experiences direct solar exposure, with observed jets resulting from sublimation of ice coating, or from controlled venting used for thermal control or attitude adjustment. Second design consideration, propulsion, and trajectory control. Any interstellar probe must navigate, must adjust course to target specific stellar systems, and to make corrections as needed during the long journey. Carrying conventional chemical fuel for decades or millions of years of flight would be prohibitively massive. But if the probe is coated with ice, either deliberately as radiation shielding or incidentally from accumulation during passage through molecular clouds, that ice can serve dual purpose as both protection and propellant. Solar heating naturally sublimates ice, creating gas that can be directed through vents to produce thrust exactly like a rocket engine burning fuel and ejecting exhaust. By controlling which vents open and when, by varying the geometry of emission to produce desired force vectors, a probe could execute trajectory modifications using the star's own energy to drive propulsion. This is essentially solar thermal propulsion, using stellar radiation to heat working fluid that is then expelled for thrust, a concept that has been studied extensively in human spacecraft design literature. The anti-tail jet, that mysterious sunward-pointing beam that we have struggled to explain through natural processes, could be thruster exhaust. If the probe needs to decelerate, needs to reduce velocity relative to the Sun during its passage through the inner system, perhaps to increase observation time or to modify trajectory for subsequent targets, it would fire thrusters oriented to produce anti-velocity thrust. Exhaust pointing toward the Sun creates force that slows the object, exactly what you would want if reducing speed relative to the star. The collimation we observe, the tight beam maintained over 500,000 kilometers, might result from magnetic nozzle focusing or from electrostatic confinement or from any of various technologies that have been proposed for electric propulsion systems that use electromagnetic fields to shape and accelerate ionized propellant. Third consideration, power generation. Spacecraft operating at interstellar distances, in the cold dark between stars where sunlight is vanishingly faint, need either radioactive thermal generators or some method of energy storage that can sustain systems for millions of years. But once entering a stellar system, once approaching the central star where solar flux increases dramatically, solar power becomes available. The stable pole-sun orientation would maximize solar energy collection if one end of the object contains photovoltaic panels or other light-harvesting surfaces. Maintaining that orientation as the probe moves along its trajectory ensures continuous power generation, avoiding tumbling that would cause intermittent shadowing and power interruptions. Fourth, communication and data relay. If the probe's purpose includes gathering scientific observations of the stellar systems it visits, or searching for signatures of other technological civilizations, or serving as relay node in Interstellar communications network, it would need to transmit information. The tight columnated jet might serve communication purpose, carrying modulated signals back toward the origin system or toward other probes or toward potential receivers. Tightly focused beams are essential for interstellar communication, where signal strength must be maximized to overcome the vast distances and where preventing spread reduces interference and improves detection at the far end. Fifth, long-duration survival. Objects traveling through interstellar space for millions of years face continuous bombardment by cosmic rays, high-energy particles that gradually damage materials and degrade electronics through radiation effects. Ice coating provides excellent radiation shielding because hydrogen is effective at stopping energetic particles, and water ice is abundant and easy to work with. A probe designed for interstellar journey would likely encase itself in ice meters thick, gaining both radiation protection and eventual propellant mass in single design element. As it approaches stars and ice sublimates, the protective coating gradually erodes, but by that point the probe has entered region where stellar magnetic field provides some shielding and where mission lifetime may be measured in years rather than millennia, so radiation damage is less critical. When we synthesize these design considerations, when we ask what an interstellar probe optimized for thermal survival, navigation capability, power generation, communication, and radiation protection would look like as it passes through a stellar system, we get an object that exhibits stable pole-sun orientation, that produces directed jets aligned with its rotation axis, that shows symmetric activity from opposite poles at different points in its trajectory, that maintains coherent beam structure over enormous distances, and that appears to respond to changing thermal conditions with coordination, suggesting central control rather than random response. Every one of these characteristics describes what we actually observe in 3i Atlas. Does this mean 3i Atlas is definitely a probe? No. It means the technological hypothesis explains observation parsimoniously, requiring fewer ad hoc assumptions than natural explanations that must stack multiple low-probability coincidences. It means we have moved beyond pure speculation into territory where artificial origin is viable, working hypothesis that deserves serious investigation rather than reflexive dismissal. But let me be very clear about what we lack, what evidence would be required to definitively confirm technological origin, and why we have not yet reached that threshold despite suggestive anomalies. We have not detected radio transmissions or other electromagnetic signals that would indicate active communication systems. We have not resolved surface structure showing geometric patterns or mechanical components, or any visual signature of artificiality. We have not measured chemical composition showing refined metals or synthetic compounds that would be unambiguous markers of manufacturing. We have only behavioral anomalies, only observations of how the object moves and emits and maintains orientation in ways that strain natural explanations and that resemble what probes would do, but that do not absolutely prove artificial construction. The December 19th closest approach, now less than 48 hours away, provides opportunity to gather data that might shift the balance of evidence decisively. Every major telescope that can point at 3i Atlas will be pointing. Every spectrograph available will be collecting data. Every high-resolution imaging system will be capturing pictures at the best resolution possible from Earth-based facilities. What are we looking for? What observations would push us toward definitive conclusions rather than leaving us in continued uncertainty? First, resolved surface structure. If we can see the nucleus directly, if the combination of closest approach distance and optimal phase angle and reduced coma density allows us to resolve the solid body rather than just observing a bright point source surrounded by gas and dust, then shape and surface properties become visible. Natural comets are jagged, irregular, heavily cratered and fractured, showing the scars of billions of years of collisions and thermal stress and tidal disruption. If 3i Atlas shows smooth surfaces, geometric regularity, cylindrical or spherical symmetry, that would be very difficult to explain naturally and would strongly support artificial origin. Conversely, if it looks like typical comet nucleus with rough chaotic topography, that supports natural interpretation even if behavior remains anomalous. Second, rotation behavior under high resolution. If we can measure brightness variations and position variations with sufficient precision to characterize rotation state definitively, we can determine whether orientation is truly stable or whether apparent stability is just a fortunate but temporary configuration. If orientation changes during the observation window, if we see the pole-sun alignment breaking as pure Newtonian mechanics predicts it should once we stop requiring multiple coincidences, that validates natural tumbling hypothesis and suggests earlier observations caught the object during brief anomalous phase. But if orientation remains locked, if sun pointing persists, even as we watch with high temporal resolution, that implies active control or passive stabilization mechanism far more sophisticated than natural comets possess. Third, spectroscopic detection of anomalous composition. If we find elements or molecules that do not occur naturally, that require technological processing to produce, that is smoking gun evidence for artificiality. Examples would include refined metals showing isotopic signatures of nuclear transmutation, synthetic organic compounds not found in natural chemistry, or atmospheric constituents that are thermodynamically unstable and could only be maintained through active management. The challenge is that most materials that technology uses, metals and ceramics, and even complex organics, can in principle form through natural processes. Distinguishing natural from artificial composition requires not just detecting unusual elements, but identifying specific combinations or isotopic ratios or structural forms that nature cannot produce. Fourth, trajectory changes indicative of active maneuvering. If 3i Atlas executes course corrections during the observation window, if we see the acceleration pattern change in ways that cannot be explained by smooth, continuous outgassing responding to solar heating, if discrete thrust events occur that look like deliberate maneuvers rather than random outbursts, that would provide strong evidence for active control. Modern astrometry can measure position changes with millisecond precision, sufficient to detect velocity changes of meters per second over observation periods of days. Any significant deviation from predictions based on passive dynamics would demand explanation and would resurrect artificial hypothesis with renewed force. Fifth, electromagnetic emissions beyond thermal radiation. If we detect radio signals, if we see structured modulation rather than just the blackbody thermal emission and scattered solar radiation that any object should produce, that would be definitive. SETI searches have been monitoring 3i Atlas for months, looking for exactly such signals, applying sophisticated analysis techniques to separate potential artificial transmissions from natural noise. So far, nothing conclusive. But December 19th provides optimal signal-to-noise conditions as distance minimizes, and as viewing geometry potentially allows detection of beam transmissions that might not have been directed toward Earth at other times. What if December 19th observations fail to provide smoking gun, fail to definitively resolve whether 3i Atlas is natural or artificial? What if we get better data, tighter constraints, more precise measurements, but still find ourselves unable to rule out either hypothesis conclusively. This is perhaps the most likely outcome. This scenario that matches how science typically progresses when dealing with ambiguous evidence at the limits of observational capability. We would be left with improved understanding of the object's properties, with better models of its behavior, with refined probability estimates for various explanations, but without the closure that definitive answers provide. In that scenario, the scientific debate would continue. Some researchers would maintain that natural explanation, however strained, remains preferable to invoking artificial origin absent absolute proof. Others would argue that cumulative weight of anomalies crosses threshold where artificial hypothesis becomes more plausible than natural, explanation requiring extreme coincidences. Both positions would be defensible given the evidence, and resolution would require additional data from future observations or from potential follow-up missions if we could launch spacecraft fast enough to intercept 3I Atlas before it leaves the inner solar system and recedes beyond range of close investigation. But there is another consideration beyond just scientific curiosity, beyond the academic question of natural versus artificial classification. There are practical implications that depend on answer, and that should inform how we respond regardless of certainty level. If there is even reasonable probability that 3I Atlas is technological artifact, if the artificial hypothesis is competitive with natural explanations rather than wildly improbable speculation, that has profound implications for humanity's understanding of our cosmic context and for how we should approach future interstellar visitors. First implication: we're probably not alone in developing technology capable of interstellar exploration. If 3I Atlas is artificial, it demonstrates that at least one other civilization achieved capability to send probes between stellar systems. That civilization might be ancient, might be extinct, might be so far away and so long ago that we will never have any contact more direct than occasionally encountering their artifacts as they pass through our system. But their existence, past or present, would confirm that technological intelligence is not unique to Earth, that the pathway from chemistry to biology to consciousness to technology to spaceflight is not so improbable that it occurred only once in galactic history. Second implication: interstellar probes might be common enough that we should expect to detect them occasionally as our astronomical survey capabilities improve. If civilizations launch probes toward nearby stars, if even a small fraction of stars host technological species at some point in their history, then the volume of space that has been visited by someone's probes could be substantial. The detection rate depends on probe lifetimes, on how many are launched per civilization, on how they are distributed across the galaxy, all parameters we cannot currently estimate. But if we have detected one through lucky chance, there are likely many more. Third implication: understanding the probe's capabilities and purpose becomes urgent question. Is it still operational, capable of responding to signals, potentially dangerous if it interprets human activity as threat? Is it defunct, a derelict drifting through space carrying only historical information about its builders? Is it observational platform gathering data about stellar systems, potentially including data about Earth and human civilization? Different purposes imply different appropriate responses, different strategies for investigation, different considerations about whether to attempt communication versus maintaining observation silence. Fourth implication: we need infrastructure to detect and track interstellar visitors more systematically. Currently, our ability to find such objects is limited, dependent on survey programs designed primarily to detect near-Earth asteroids that pose collision risk. We find interstellar visitors essentially by accident, when they happen to pass close enough and bright enough to trigger detection algorithms. With dedicated surveys, with space-based infrared telescopes that can detect heat signatures, without relying on reflected sunlight, with expanded computational resources for analyzing survey data, we could potentially detect dozens or hundreds of interstellar objects per year rather than one every few years. If some fraction are artificial, systematic survey would provide statistics on frequency and properties. Fifth implication: we should reconsider our assumptions about what is possible or probable in cosmic evolution. The strong anthropocentric bias in human thinking is to assume we are typical, that our developmental pathway represents normal or average progression for intelligence. But if we encounter artifacts from civilizations far older or more advanced, if we find evidence for technologies we have not imagined or capabilities we consider impossible, that should drive humility and openness to possibility that our frameworks might be parochial, limited by our specific history and by the narrow slice of physical parameter space we have directly experienced. Now, in these final moments before we enter the critical December 19th observation window, I want to directly address you, the audience following this story, because your engagement matters in ways that extend beyond just staying informed. Science is not just professional activity conducted by credentialed researchers. It is collective human endeavour to understand reality, and that endeavour benefits from broad participation, from diverse perspectives, from public attention that motivates investigation, and that demands transparency and intellectual honesty from institutions. If you have found value in this analysis, if the detailed examination of evidence and probabilities and physical mechanisms has helped you understand why 3i Atlas is generating such intense interest and concern, then you can contribute to collective investigation in several ways. First and most important, share this content widely. Most people have no idea this is happening. Mainstream media coverage has been minimal, brief mentions in science sections noting unusual comet, without engaging with the profound mysteries that detailed observations have revealed. The story is flying under radar, known primarily to specialists and to the small community of people who follow astronomy developments closely. But this could be the most significant astronomical event of our generation, potentially the first confirmed detection of interstellar artifact if artificial hypothesis proves correct. At minimum, a revolutionary example of natural phenomena that challenges our understanding of planetary science, if natural explanation prevails. Everyone should have opportunity to follow the story, to examine the evidence, to participate in collective investigation. Sharing this video, posting it to social media, sending it to friends and colleagues who might be interested. These actions expand the audience and ensure that important developments receive the attention they deserve rather than being ignored because they do not fit convenient media narratives. Second, engage in comments section. I want to hear your perspective. What do you think after reviewing all the evidence? Natural comet exhibiting extreme but ultimately explicable coincidences? Artificial probe demonstrating that we are not alone in achieving interstellar capability? Something else entirely? Perhaps some middle ground where the object is natural but exhibits properties that force us to expand our categories and recognize new classes of phenomena. The discussion benefits from diverse viewpoints, from people with different backgrounds and different areas of expertise contributing insights. No one person or institution has monopoly on truth. Science advances through collective critical examination. Third, if you have observational capability, participate directly. Even modest amateur telescopes can detect 3i Atlas during closest approach, can measure position for astrometry contributions, can monitor brightness for rotation period refinement, can capture images that document the object's appearance from different locations and different viewing angles. Citizen science is increasingly important in astronomy, where professional facilities cannot observe everything continuously. Your data, submitted through appropriate channels and combined with thousands of other amateur observations, builds comprehensive datasets that enable robust conclusions. Fourth, hold institutions accountable for honest investigation. If evidence continues accumulating that challenges natural explanations, if observations become increasingly difficult to reconcile with passive comet hypothesis, public pressure can help ensure that artificial possibility receives serious consideration rather than being dismissed reflexively because implications are uncomfortable. Science works best when it follows evidence honestly regardless of where conclusions lead. Public attention and engagement help maintain that honest pursuit even when powerful institutions or established paradigms resist acknowledging anomalies. Fifth, support missions and programs that would allow closer investigation. If 3i Atlas departs and recedes beyond detailed observation range, while questions remain unresolved, we will have lost opportunity that may not return for years or decades until another interstellar visitor appears. But we could potentially launch interceptor missions, fast spacecraft that could rendezvous with the object before it leaves inner system, that could conduct close flyby observations or even soft landing to return samples. Such missions are technically feasible with current propulsion technology, requiring political will and funding allocation rather than awaiting technological breakthroughs. Public interest and advocacy can help move these concepts from study phase to actual implementation. Now let me address what happens after December 19th, after the critical observation window closes and data has been collected and analysed. Results will not be instantaneous. Professional astronomy moves deliberately, carefully verifying measurements and conducting peer review before publishing definitive conclusions. But preliminary results will leak, will appear in astronomers' bulletins and conference presentations, will be discussed in online forums by people with access to raw data. We will be monitoring all these channels, synthesizing information, reporting findings as they emerge. Subscribe to this channel if you have not already. Enable all notifications because the story continues beyond closest approach. Analysis of December 19th observations will occupy researchers for weeks or months. Additional observations will occur as the object recedes, tracking how properties change with distance and time. Debates about interpretation will intensify as better data constraints competing hypotheses. We will be here covering every development, examining every new piece of evidence, maintaining the detailed technical analysis that has characterized this coverage from the beginning. Whatever we learn from 3i Atlas, whether it proves to be extraordinary natural phenomenon or unprecedented artificial detection, or something that defies simple classification, it will teach us about what exists in the universe beyond our immediate experience, about the diversity of objects traveling through the galaxy, about whether intelligence and technology are common or rare features of cosmic evolution. That knowledge, that expanded understanding of our cosmic context, is precious regardless of specific answers, valuable for how it shapes our perspective on humanity's place and prospects, and long-term future as we contemplate our own potential to eventually become interstellar civilization sending our own probes to other stars. We stand at threshold of discovery, in that pregnant moment before answers arrive, when possibility remains open and when careful observation and honest analysis might reveal truths that transform understanding. Less than 48 hours now. Every hour that passes brings us closer to data that could resolve mysteries or deepen them, that could provide closure or generate entirely new questions that could confirm our comfortable categories or shatter them beyond recovery. The telescopes are ready. The observers are prepared. The computers are configured to capture and process torrents of data that will flow from instruments. Worldwide, 3i Atlas continues its rush through our solar system, oblivious to human attention focused on it, following whatever trajectory physics or design has determined, exhibiting whatever properties nature or engineering has given it. We will watch, we will measure, we will analyze, and we will learn, because even in uncertainty, even without definitive answers, the process of careful observation and rigorous reasoning advances our collective knowledge and reminds us why we look up, why we study the night sky, why we invest resources in understanding cosmos that operates according to laws we did not write, and that contains wonders we are only beginning to comprehend as our technological capabilities expand and as our curiosity drives us to ask harder questions and to accept uncomfortable possibilities and to follow evidence honestly wherever it leads, even when destinations challenge everything. We thought we knew about what is possible and what is actual in universe that remains far stranger than our theories predict it should be. Thank you for following this investigation. Thank you for engaging with complexity rather than demanding premature certainty. Thank you for being part of the collective human effort to understand this mysterious visitor from beyond. Like this video, if you found it valuable, share it widely so others can participate. Comment with your thoughts and theories. Subscribe and enable notifications for continued coverage. And watch the skies because they are speaking, telling stories through light and motion and behavior, stories that we can read if we pay attention, and if we remain open to messages that might challenge our assumptions, but that ultimately expand our understanding of reality as it actually is, rather than as we wish or expect it to be. I will see you in the next update as the countdown reaches 0 and as December 19th reveals whatever truths it holds.